2. What is the common ion effect? So, ion effect. What is that? So, let me give you a scenario, okay? So let's say you have a solid that's forming like a Ca. Trying to think of something that's kind of soluble. CaSO3, something like that. No, actually, CaSO4, calcium sulfate. I believe that's what it is. And you know, some of it dissociates to form the calcium and the sulfate. Okay. So, with this, all right, this is what we have. The most of it would be solid because calcium sulfate, if I remember correctly, isn't too soluble. But this is what we'll be getting. Now, let's say we threw in specifically a completely soluble thing. Usually things with sodium are really soluble, but sodium sulfate. We threw that into the mix. So, as a precursor, actually, before that, this right here, this formula here, was, let's say we had a beaker, okay? It was just water, okay? Hence how we have the aqueous solution, and we threw the CaSO4 in. Okay, that's what happened here. Now in the situation where we have the sodium sulfate, okay, now we have the beaker, right? But there's already sodium and sulfate in it. The common ion effect is pretty much stating that when there are ions that are shared in the solution, or like there's things that are being in compounds that are being mixed, there's less products formed, as in it's going to go in the direction that would favor it having less ions in the solution, because now, because the sulfate's in there, right, this calcium sulfate isn't going to form as much of its own. So you notice that the this equation here, this solution, will actually go towards the reactants. You end up seeing more solid in the solution because it cannot dissociate, because there's a common ion, sulfate, in that solution. That is, in a sense, the common ion effect. One of these principles that actually does discuss it, as it actually mentions here, is Le Chatelier's principle. I spelled it wrong. Okay, and this principle pretty much says that, like, in equilibrium, right, there are certain things that change it. Concentration is one, which is what's happening here, and pressure is another one, and also concentration, pressure, and temperature. Those are the things that really mess up equilibrium. And in this specific example here, we're dealing with concentration. So what's happening is that now that we have an increased concentration of sulfate ions, okay, when you increase what's in the product size, your reaction shifts towards the reactants. Okay, now let's say there's a situation where I'm trying to think, like there's some way we could actually extract this carbon out, this calcium out, so somehow we were able to actually get this down. If that happened, then you notice that the reaction now will actually favor the reactants. More of this solid will dissolve if we're able to somehow extract the calcium ions. That is, in the sense, the Chatelier's principle, is that as concentration changes, the equilibrium will change as well. So that's not what we're focusing on here. We're focusing just on the common ion effect, which means that now there's two common ions, well, just one sulfate, but it's present in both of them, sodium sulfate and calcium sulfate. So with that, there's an increase of sulfate pushing the equation back to the reactants, meaning that we have less sulfate being produced from this calcium sulfate. Okay, so that is, in the sense, a common ion effect. Let's see how we did here. Yep, it does mention the Chatelier's principle as we discussed. So exactly, concentration, pressure, and temperature. Yes, feels good to get that right still. And they chose a much easier explanation. Actually, I like this one better because calcium sulfate, I don't remember if that dissolves, but this one is a good example because we have here hydrochloric acid in water, and it separates into hydronium and chloride. So if you actually threw in some salt in there, sodium chloride, you'll notice that the hydrochloric acid, although it is a strong acid and likes to dissolve completely, there's competition in terms of now we have some chloride already present in there. The only issue with this example is that there are some things that have extremely high, I guess, ionizing capability, like their K value. Pretty much it means that, you know, when you put it in water, they like to completely separate. So even though it's in the presence of sodium chloride, in this example here, it'll still most likely produce just as much of the H3O and Cl minus, just because that's how much it likes to disassociate in water. The K value is way above 1, and usually when you have a K value above 1, you're going to dissociate. This calcium sulfate, though, in this example, so I guess this still works, its K value is less than 1, a lot less than 1, hence why it doesn't do so well in dissolving, which is why this would be a better example of the common ion effect, because now it already doesn't want to dissociate, and now it has even less reason to dissociate because there's already some sulfate in there. Okay, so with that, this is still correct because this does a great but watch out for K examples chosen. Some things dissociate no matter what. Okay, so with that, let's move on to question 3. Okay,